Hello and welcome back to Calculus 1 section 3.3 on rules of differentiation. First off, the word differentiation is the process of taking the derivative. Is the process of taking the derivative. Now, that necessarily means you are changing the function. So, I'll write this down. Functions change numbers. So, you have x coming in, then the function acts on it and the y comes out. So you might plug in 3 and you get on the outside 17 or whatever, right? So that's just simple y equal f of x, where when you plug in certain x, y changes, function changes it into a y, so you get a different value. You can get the same value, but in general it's different. Derivatives change functions. So you plug in f of x, then you differentiate, and out comes f prime, which is, except in one case, always different than the input function. So that's very important. The earlier example that we just saw, I believe it was an exam, right? It was that the derivative of 2x squared plus 2x was 4x plus 2. Right? So this one over here is f of x, and this one over here is f prime of x. And you see they're different functions. This one is a parabola that opens up, graph like that, and this one is a linear line that graphs like. So they are completely different functions. Yes, they're both polynomials, but they are different functions. So derivatives change functions into different functions. And we learned that there is a relationship between these functions through those tangent lines and slopes and measurements of a change and all of that good stuff that we covered in 3.1 and 3.2. Now, the goal for today is to learn the shortcut methods of taking the derivatives, so you don't have to mess with the limit every time you need the derivative, and you need the derivative a lot. Anytime you want to measure the change, you are taking the derivative, and that would mean you have to crank the limit with, the age and all that good stuff. But throughout the years, the patterns emerge, and we now know that there are faster ways to take the derivatives, which is what you asked about, right? Because you want to find the derivatives the faster way. Now, that means you will have to memorize the formulas. And that concept should not be strange to you because you memorize multiplication tables, right? Do you have to know them? No. You can go 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. Good. Or 3 times 5 is 15. You chose to memorize multiplication tables, so you don't have to add all these numbers all the way up to, right, the value you're looking for. So you memorize. So now you are going to be offered these formulas, and you either memorize the formulas or go ahead and crank the limit every time. So these formulas are going to take the limit out of commission, and you will be using formulas because those are shortcut formulas. And if you don't want to learn the formulas, then you will have to crank the limit every time. And for some of these, the limit is not easy at all. So let's take a look at the formulas that you need to memorize. First one is obviously the derivative of a constant is 0. there is no change in a constant, and because there is no change in a constant, the derivative is 0. Put that one on a cloud, and put some examples. The derivative of 7 is 0. The derivative of pi is 0. Pi over 2, pi over 7, whatever you want to put. All of these derivatives are 0. What you are seeing here is what I earlier called Leibniz notation, which is notation that allows you to have the derivatives in line with the function. The other way to write this is to say that your f of x is equal to a constant c, and then you have to go to the new line and say that the derivative is 0. These two things say the same thing, except the upper one, everything is in line. You have your derivative of this function is that function. So it's in line. Where over here says function is this, the derivative is that. So you cannot make the choice which notation you like better, and you can stick to it 100% of the time. My preference is obviously Leibniz notation because everything is in line and I don't have to write a lot. I can just go and have everything in one line.
Why even teach the other way then?
Because there are certain cases when it's useful, and then mechanical engineering prefers. It's just, we have two. Take linear algebra, we're going to have different one. And then there's going to be another one in Calc 3. So yes, you're going to see so many of these notations, but currently these are the two that you want. So the Leibniz notation, and then you have f prime, then you have y prime, mechanical engineering y with a dot, which is original Newton notation, and then capital D for linear algebra and so on. So a whole bunch of different notations for the same thing. Because calculus was developed in few regions at the same time, and they used different notation because they didn't know about each other, right? Next one, the derivative of x to the n is nice. Boss. Put that one on the cloud. Guys, this one takes care of 3 different types of functions. So we have n is let's do n bigger than 0 first. So if n is larger than 0 and whole number, we have polynomials. Like, let's say x to the 9. If n is less than 0 and the whole number, we have rational functions. Like 1 over x cubed, which is x to the minus 3. You see that? And if n is a fraction, we have radical functions. So you have, let's say, something like this. That will be x to 1/3. So you can see that polynomials, rational, and radical functions are all represented by this one rule that you have to memorize. And now you can go and say, what is the derivative of x to the 9? Well, the formula clearly says whatever your n is, drop it down which is 9, and then you have x to the 9 minus 1, which is 8. And you're done. That's it. If you are to do this with a limit, you would have to FOIL x plus h to the 9th, right? So you don't want to use limit for these. The shortcut formulas are there to make your life easy. Let's say there is 1 over x to the 6. You rewrite that using algebra as x to the minus 6, and then you apply the same formula. Drop down the n, and then subtract 1. So that's negative 6, x to the negative 7, and then make it into a positive exponent by kicking the negative exponent down. So we have negative 6 divided by x to the 7 when it goes down. So the same rule deals with these. And let's do the cube root, the one that I mentioned earlier. So cube root of x is going to be the same as the derivative of x to the 1/3. Use the formula, so 1/3 drops down. X to the 1/3 minus 1 is negative 2/3, which is 1 over 3 x to the 2/3. And we leave it there. Now, there are two particular functions that will be around for many examples over and over and over again. So even though the rule belongs here, people generally tend to memorize them because they are, it's much faster than, use the rule and so on. And that's the derivative of square root of x, which is 1 over 2 root x. Now, obviously, you can use the rule to show it and prove it. And another one is d dx of 1 over x, derivative of 1 over x, which is negative 1 over x squared. So these are your convenience formulas. I'll put them on a cloud. Let's box them up. Quality of life formulas. How about that? Because by the time you rewrite x as x to the 1 over x as x to the minus 1, and then you apply the formula, it's much faster if you just know it. So that's our polynomials. So far, we took care of the constant, the derivative of any constant, any number, whether it's a fraction or a rational, irrational, whatever it is. The derivative is 0 because constants do not change. Derivative measures change. Constants don't change. Therefore, the derivative of constant is a 0. And then we have x to the n, which can give us three types of functions: polynomial, radical, and rational. The next creature is going to be e to the x. The derivative of e to the x is itself e to the x, and because of that, not too interesting, because it doesn't change. So that's the one special function that does not change under the differentiation. Now, we generally use e to the ax, like e to the 2x, e to the 3x, e to the 5x, right? So that a is a number, and the derivative of that is a e to the ax. So generally, that's the one that we use about 90% of the time, maybe even more. this one. So the derivative of e to the 3x is 3e to the 3x. The derivative of e to the x over 2 is 1/2 e to the x over 2, because the constant that it's multiplying x is 1/2. So your a is 1/2 and just plug it in. So all of that, not a big deal. How about the derivative of e to the pi?
Yes.
Sunny?
That's a constant, that's 0.
Yeah, I saw. Yes. It's a constant. Yeah. Nice. I saw you mime it. 0. Because e is a number, pi is a number, and then e to the pi, that's just a number. Punch it in a calculator. You're going to get decimals. The derivative of constant is 0. So no x, so not a function. If you are struggling with that, there you go. Now if you want to make a function out of it, you can. E to the pi x, there you go. Now it's pi e to the pi x. Oh, it's all good. All right? We can salvage it. Great, we're done with the e. What else is left? The derivative of ln of x is 1/x. The derivative of ln x is 1/x. No examples there, because that's it until we learn more about this. Now a student said, well, can't we just have ax? Sure, but it doesn't change the situation. I'm just going to remind you, right? Yeah, because the derivative of ln ax you can rewrite as using basic algebra, right? As ln a plus ln x. And the derivative of ln a is 0, because just derivative of a number plus 1/x. So you still get 1/x. Having a number in front of x within ln doesn't change anything. Now, can you have a different thing than x? Sure, we are going to have ln of sine x, ln of tangent x, ln of, right? So eventually, not today. Maybe on Wednesday. Maybe on Wednesday. We're going to make this interesting, but now it's just one basic formula that you can't really change in any way. So I'm going to put these formulas on the board. We're going to put some rules of differentiation, and then we can finally do a whole bunch of examples. So we have the derivative of the constant is 0. Derivative of x to the n is n x to the n minus 1. The derivative of e to the ax is a e to the ax, and finally the derivative of ln x is 1 over x. So these are the formulas, the rules, and now the formulas for differentiation are all in one spot. Clearly trig is missing, but that's going to be the separate lesson, and then inverse trig is going to be separate lesson as well. Chapter 3 has 11 sections to it, so it's double the size of your chapter 2. It's the largest chapter actually in the calculus book, chapter 3. So there you go. All right, so now some properties. Properties of derivatives. Number 1, the derivative of f plus g is the derivative of f plus the derivative of g. And the second one is the same with minus. This means that you can do derivatives term-wise. So the derivative of f minus g is the derivative of f minus the derivative of g. Number 3, the derivative of c times f of x. So if you multiply a constant, you can kick the constant outside and then do the derivative of f. Only. So these are your properties. The first two simply state that each term in the differentiation is to be done separately. And then the third one says if there is a constant in front of the function bothering you, just kick it out. And then whenever you find the derivative, multiply by that constant. So let's take a look first at the constant, because that's the one that is more frequent, right? Let's say you have 6x to the 4. So the rule number 3 says you can kick 6 outside, take the derivative of x to the 4, and you know the formula for that, right? And then whatever you get, multiply by 6. So it's going to be 6 times 4x to the 3, which is 24x to the 3, and you are done. So the rule for the constant is kick it out. Do you have to? No. Very soon you're going to go just, 4 times 6 is 24, and then 4 minus 1 is 3. So you're going to have 24x to the 3 just by looking at it. But again, that's homework and practice, and you will not be writing all of these steps. But it's coming up in 15 minutes. Not even. Called the second derivative, third derivative, fourth derivative, so that you can go from position to velocity to acceleration to jerk and so on. So we'll get there. The derivative of 3 over x. The derivative of 3 over x. You kick 3 outside, and then you just have the derivative of 1 over x. Oh my God. No.
The rule of the
Yes. So, x to the minus 1, then subtract. I mean, you can.
1 over x squared.
You can, if you memorize that one, sure. So, negative 1 over x squared. So, the whole thing is negative 3 over x squared. Cool? Of course, calculus. So what is the derivative of 2x squared plus 2x? So we kick 2 out, then we have the derivative of x squared, then plus, kick the 2 out, and then we have the derivative of x. So what is the derivative of x squared? 2x plus 2 times, and what's the derivative of x? 1. Derivative of x is 1 because exponent will subtract 1. My exercise for today. There we go. There we go. So the derivative of x is 1 because you got x and then the exponent is 1, drops 1 in front, and then you have 1 minus 1, which is 1 times x to the 0, which is 1 times, right? So the derivative of x to the 1 is x to the 0, which is 1. Good. So we have that, and there you go. 4x plus 2, as you have foreseen. Charge. Here's something for you guys to enjoy. So how about 4x to the 6 plus 3e to the 2x? Yep, you break them down into 2 separate. You kick out 4, you kick out 3. Yep. Go ahead. Have fun. So 2 separate derivatives. First one, kick out 4. We have the derivative of x to the 6 plus kick out 3, the derivative of e to the 2x. Oh, I forgot the derivative. Oops. There's a ddx right there. Mushed in. So now we have 4 times 6x to the 5 plus 3 times 2e to the 2x, which is 24 x to the 5 plus 6e to the 2x.
Yeah, I got it right.
The first one of many.
Let's do this first.
The limits lead into this, to 3.1, right? And the derivative of 4th root of 9x to the 3. Because we can. Let's see what you get. No coughing. So what's the constant that we kick outside?
9. Wait, 9x to the 3rd. Kick that all
You have a 4th root of 9.
So then it'd be
So it's gonna
9.
4th root of 9, and the 4th root of 9 is root 3. Because 4th root is like root under the root. So 4th root is the same as root under the root. And if you have a 9, then square root of 9 is 1 square root will be used up to transfer 9. So root 3 gets kicked out, and then we have the derivative of x to the 3/4. I hope you wrote the constant thing, so I'm going to erase it. 3, 2, 1, gone. So I have a root 3, and then I have 3/4 x, 3/4 x to the -1/4. So this becomes 3√3/4 times 1/4 root of x, and then put everything on the same. There we go. It's just annoying as hell. That's all it is. Yeah. It's called flexing in mathematics. There's no reason for it whatsoever. It's just we can do it, so let's. Right? That's all it is. That's all it is. Alright, so now what we're going to do is we are going to go into higher order derivatives, which is what you were asking about. Higher order derivatives, which means that you can take the derivative of the derivative, and then you can take another one, and another one, and another one, and another one. And in some cases, right, your function is going to go to 0 and disappear. In other cases, it's going to continue existing forever. So higher order derivatives are the second derivative, third, fourth, fifth, sixth, seventh, and so on. Generally, in application, we use up to 3, but can you take a 27th derivative? Yes, you can. You just have to get all the 26 derivatives prior to that one. Because whatever derivative you are taking, it's always the derivative of the previous derivative. So if I have the function f of x, then I take the derivative and I'll get f prime of x, that's the first. Then f double prime of x is the second. Then f triple prime of x, which is the third. And then notation changes into parentheses like this. And you put the order of the derivative in the little, right, and it can go forever. So if I have that x squared is, let's say, 3x to the 4th minus 12x squared plus x minus 6, we take the derivative and we get 12x cubed minus 24.
Bless you.
Oh, thank you, I feel blessed. Plus 1. Because the derivative of x is 1. Yes, the derivative of negative 6 is 0. So now for the second derivative, and this is where we start studying our higher order derivatives, we take the derivative of the first derivative to get to the second derivative, and that's going to be 36x squared minus 24, and then the derivative of 1 is 0. The next is 72x. The next is 72. The next is 0, right? And from this point on, for this particular problem, all other derivatives will be 0 forever. Yes? I'm always taking the first derivative. Mm-hmm. You take the derivative to get to the next one.
So what's a practical application?
Physics, engineering, everything we have. Because your position function, its derivative is velocity, its derivative is acceleration, its derivative is jerk. There's more, but these are the ones that you will study in physics. And taking derivatives measures things. Now in economics is also used for concavity to see whether you are losing money or gaining money, not as increase and decrease, but over time. We are eventually going to learn that as well in this class. So next class, we are going to have the section in which we are going to use these things. So this is our higher order derivatives. We can get different examples. So say f of x is equal to e to the x. What's a 123rd derivative of this function? E to the x. Good. How about a little bit spicier example where you actually have to think? If I tell you that f of x is equal to e to the 2x, and I am asking for, let's say, 100th derivative. So we do all agree on e to the 2x, we just don't agree on a constant here. What happened? Every time you take the derivative, what happened? What pops up? A 2.
Yeah, 2 times.
2 to the power of 100, nice. Because you're going to pop out 100 2's. If you take 100 derivatives, every time you take a derivative of e to the 2x, it's going to pop out a 2. So you are going to pop 100 2's out, so 2 to 100. So this is one of those, again, flexing in math, we can do it. So let's do it. Great. And the final example of this would be the derivative of 1 over x. Now, when you have this one, you will see the powers rise, because every time you do the derivative, it's minus 1. So it was negative 1, next time is negative 2, then the negative 3, negative 4, negative 5. So the powers are going to grow in denominator. We already know that the first derivative of this is negative 1 to x squared, because we did that earlier. And now the second derivative is going to have 2 over x cubed. How do you get that? Well, you rewrite this one as negative 1 times x to the minus 2, and then when you take the derivative, you have negative 1 times negative 2 is positive 2, x to the negative 3, and that simplifies into 2 over x to the minus 3. Third derivative is going to be negative 6 over x to the 4th. And going down forever, you see that from 1 over x, right? So x squared, x cubed, x to the 4th. So the more derivatives you take, the more the powers grow in the negative sense, right? And you keep having rational functions forever. So that one is not going to go to 0, right? And it's using the same and xn minus 1 rule like the polynomials. So polynomials do go to 0. So just take, one step at a time. You practice, obviously, the vanilla problems, and then you go into these derivatives. Now, before you freak out with the notation, I have to show, because you will run in the homework, right? You will run into the notation. So you want to know when you see it. So the notation I have been using so far let's put a title. Notation. Notation I have been using so far, d dx of f of x gives me f prime of x is read the derivative. There's a times over here, which is always read as of. And then this one over here is f of x, the function. So the derivative of the function, and then is, and then you have the f prime, right, which is the derivative, which is a different function. So when you are reading the notation, you always say the derivative. Now what you also can say over here, in respect to x, because it's d over dx. Now this is going to play a huge role in Calc 3 when you have mixed partial derivatives and all these kind of things, so you have to be very careful. Over here generally it's always the same variable because it's a single variable. So what's happening now if I have second derivative and more? So now if I have a second derivative, f double prime of x is denoted as d squared dx squared of f of x. And this notation makes a lot of sense, because if I have d dx of f of x, square and square, to start off with, I can break this down into d dx of d dx of f of x, and now you see that the inner one gives you f prime, first derivative, and then in the second step you have this one, which is f double prime. So you apply the inner derivative, and d dx is, and literally d times d is d squared, dx times dx is dx squared. So in the notation, you peel off one of the derivatives, you apply it, and that's you taking the first derivative, and then for that one you take another derivative. So this can be done in the Leibniz notation as well. It's just more writing, so generally we don't use it. But what is the second derivative of e to the 4x? Well, when we break it down into two first derivatives, you are going to first find 4e to the 4x when you take the first derivative, which is the inner one, and maybe I can color code that using the orange. And then we take the second derivative, which is another first derivative here, so that's going to be now 16e to the 4x, and that's going to be the green. The blue. No, the green. Let's use the green. So that's everything. So this notation can be also used. Generally, people like f double prime, y double prime, but you know, you can use this one as well if you want to. And I don't care what you use. So you can use f double prime of x, same as y double prime, same as d squared over dx squared of the function. All the same means second derivative. For higher order, you keep stacking. So what is the fourth derivative of x in terms of Leibniz notation? It's going to be d4 dx to the 4 of a function f of x. And if you really want to write out the string, you can. d dx, another d dx, another d dx, and another d dx. Those are all of your, that's 1, 2, 3, 4, right, for the fourth derivative. And then you have finally your f of x, and then you have to close all of these. So here's your first derivative, second derivative, third, and the fourth as you go from inside out.
You got one too many. You got one too many brackets.
One too many brackets?
Just the one.
Thank you.
You scroll over.
Sure. I did. Even better is I can. That's it. I hope you're not disappointed. Yeah, that's it. Okay. Let's take a break.